Welcome to What You Don't Know You Don't Know, the podcast that dives headfirst into the surprising, the overlooked, and the misunderstood. Hosted by a curious duo and one man, one woman, we explore the world's most fascinating ideas hiding in plain sight. From science and religion to politics, psychology, history, and everything in between, we shine a light on the knowledge that's publicly available but rarely discussed. Each episode is a deep but never dull conversation that challenges assumptions, sparks new perspectives, and reveals just how much more there is to know, especially about the things you didn't even know you were missing. Whether you're a skeptic, a seeker, or just someone who loves good conversation, this show will leave you thinking, questioning, and most importantly, knowing.
Okay, let's dive in. Think about this for a second. Something that ticks like a clock forever.
Yeah.
But with no battery, no winding, no energy input at all.
Right, a kind of perpetual motion.
Exactly. And not just arranged neatly in space, but ordered in time. It sounds, well, frankly impossible, like those perpetual motion machines physics says can't exist.
Mm-hmm.
But what if, just maybe, something like it could exist, something that genuinely breaks the symmetry of time as like a stable form of matter?
Well, that's the core kind of mind-bending idea of a time crystal. You've hit it.
Yeah.
It's a system, the idea goes, that shows this stable, repeating motion.
Oh,
Not because you're kicking it constantly or it's, winding down, but intrinsically, just part of what it is, forever, even totally isolated.
Which would mean it breaks, what's it called, time translation symmetry.
Exactly, time translation symmetry.
Is that like how a normal crystal, salt or quartz, breaks spatial symmetry? Like if you shift it just the right distance, it looks the same?
Precisely. A regular crystal has this repeating pattern in space. Move it by its lattice constant, looks identical. A time crystal, conceptually, would have a pattern repeating in time.
So you look at it, wait a bit, look again, and same state.
Kind of, yeah. But doing that in a stable way for a big macroscopic system, well, that's way, way tougher than breaking symmetry in space.
Yeah.
And that's really what this detailed review paper we're digging into explores.
Okay, right off the bat then, why? Why is time so different? What makes breaking symmetry in time so much harder? What's the fundamental roadblock the source points to?
The core problem, and this is central, really gets down to how stuff usually behaves over time. Our mission here, kind of guided by this paper, is to unpack what a true time crystal is supposed to be, scientifically speaking,
Right.
How you'd find one, why they're so slippery, and the biggest hurdle, it's thermalization.
Thermalization. Everything just kind of settling down, getting messy, reaching room temperature.
Exactly that. Systems in thermal equilibrium, that's their definition almost, they just stop changing macroscopically. Think about a cup of coffee cooling down.
Okay.
Once it hits room temperature, it's done. It sits there. Its properties aren't changing over time anymore. It's forgotten it was ever hot. You can't tell how long it's been there just by looking.
Right, time independent.
Yeah. So to break time symmetry, you need something that stays intrinsically, robustly out of equilibrium. Not just for a bit, but like forever, at late times.
Okay, but hang on. What about like a simple pendulum? The physics 101 idealized one. No friction, just swinging back and forth forever. Isn't that stable, repeating motion?
Good question. But that's where the definition gets really specific, and the source stresses this. It has to be a many-body system, macroscopic.
Maybe a buff. Okay, why?
Well, yeah, that ideal frictionless pendulum, Bob, like in figure 2A in the paper, that schematic, it swings forever. But a real pendulum, it's made of zillions of atoms. Even if you could isolate it perfectly, that initial swinging energy, it wouldn't just stay in that nice, big back-and-forth motion. Thermodynamics tells us that energy would leak. It would spread out into all the tiny jiggles and vibrations of the atoms themselves. Heat.
So it thermalizes internally. The swinging just stops, like figures 2B and 2C show.
Exactly. It just kind of fizzles out into heat, settles down, equilibrium wins. So that simple oscillation, it's not a robust property of a whole phase of matter. It just gets washed out by thermal effects in anything complex.
Got it. So it's not stable in the way needed for a whole new state of matter.
Precisely. To have a real phase with broken time symmetry, something fundamental, not just a temporary wiggle, you need a many-body system where this time-dependent stuff keeps going indefinitely, even as the system gets infinitely large, in theory.
Wow.
And crucially, it has to be conservative. No sneaky energy input needed, no energy leaking out, just ticking on its own.
That sounds incredibly demanding. The requirements are super strict. So let's nail it down from the source. What's the official definition of a true time crystal that ticks all these boxes?
The paper gives a very sharp definition. It's a stable, macroscopic, conservative clock.
Stable, macroscopic, conservative. Okay, those words hit differently now?
Yeah, they carry weight. Stable means it's a real phase of matter, not just some delicate setup. It should be robust if you change things slightly or start it a bit differently as long as you're still in that phase.
Okay.
Conservative, super important. No battery needed, no winding, no external driving force constantly pumping energy in, unlike your wristwatch or even that pendulum needing a push.
Mm-hmm.
And macroscopic, it's got to be a collective thing involving loads of particles, not just one or two things oscillating. It only really makes sense mathematically in the limit of a huge system.
These are, wow, incredibly tough conditions. Where did scientists even start looking for something that could possibly fit this bill?
Well, these constraints basically forced researchers to look beyond the usual equilibrium physics. And the big theoretical idea, the breakthrough really highlighted in this review, comes from looking at specific kinds of quantum systems, ones that somehow manage to avoid thermalizing.
Okay.
And that brings us to this concept called many-body localization, MBL.
MBL, right, I've heard of this. That's the thing where disorder, like randomness in the system, actually stops it from thermalizing. Seems totally backwards.
It is counterintuitive, absolutely, but that's the key insight. MBL happens in quantum systems that have interactions and enough disorder. Normally, energy and information just spread out everywhere, right? That leads to thermalization, like figure 2C again.
Yeah.
But in MBL systems, the disorder kind of traps things. Energy, particles, information, they get stuck locally. The system just fails to act like a good heat bath for itself. It remembers its initial state, potentially forever. You see that localized idea in figure 2.
So MBL is like finding a loophole in the laws of thermodynamics. It prevents the system from just settling into that boring, unchanging equilibrium state.
In this context, yeah, that's a good way to think about it. It provides that essential ingredient. A stable, long-term, non-equilibrium state in a closed, conservative system. Exactly what you need if you want a time crystal to survive.
The source mentioned time glasses, too, related to MBL. How are they different?
Good catch. Yeah, so if you have MBL in a static system, one where the energy landscape isn't changing externally, you can get purely temporal weirdness, like different parts might oscillate on their own clock, out of sync.
Okay.
But they usually don't have that large-scale spatial order like a regular crystal. So the source distinguishes these, sometimes calling them time glasses. A proper time crystal, the definition implies, needs both.
Yeah.
Order in space and order in time, spatio-temporal order.
Okay, so MBL stops it from dying out, but where does the regular ticking, the clock-like part come from? That sounds like it needs some rhythm.
That rhythm usually comes from driving the system externally. And that leads us to another key concept, Floquet systems. Floquet, yeah. Floquet. These are quantum systems that you deliberately poke or modulate periodically in time. The Hamiltonian, the thing describing the system's energy and rules, repeats itself after some time t. So ht is the same as ht plus t.
So you're basically kicking the system rhythmically, like pulse, wait, pulse, wait.
Exactly. You're imposing a beat. This gives the system a built-in discrete time symmetry. It only looks the same under time shifts that are multiples of your driving period t, not just any old time shift like a static system.
Okay, but wait. If you just drive a normal interacting system, what happens? Does that make a time crystal? Because earlier you said things just thermalize.
Usually no. It does the opposite. If you take a generic interacting Floquet system and just drive it, it tends to just soak up energy from the drive, like indefinitely.
Oh.
It heats up and heats up, eventually reaching this sort of featureless, infinitely hot state. And in that state, it basically just oscillates perfectly in sync with your drive. It doesn't show any independent, interesting dynamics beyond just following the beat you're giving it.
So driving it normally actually kills the special non-equilibrium state you need. It forces synchronization.
Right. Which brings us to the really clever bit, the core theoretical idea this review focuses on. You combine the two.
Driving and MBL, the Floquet MBL time crystal.
That's the one. The big theoretical insight is that these periodically driven MBL systems can actually host stable, macroscopic time crystals. The MBL property acts like a shield. It stops the system from just absorbing energy endlessly from the drive and heating up.
Ah, so MBL protects it from the drive, letting it maintain a non-equilibrium state even while being kicked.
Exactly. It locks the system into a stable, but still time-dependent, non-equilibrium state that can have its own rhythm.
Okay, this has started to click. MBL provides the stability against thermal death. Floquet driving provides the rhythm.
And the source points to a specific theoretical model where this magic is predicted to happen. A driven, disordered chain of spins, kind of like tiny magnets, an Ising chain.
Okay.
This system, under the right conditions, can enter a really weird phase. It's called the spin glass phase, or SG.
Pi spin glass. Sounds mathematical.
Ah.
What's special about this SAS-SG phase for time crystals?
What's predicted is that this phase spontaneously breaks two symmetries at once. It breaks the usual spatial symmetry, like the spins lining up in some pattern over long distances, and it breaks the discrete time translation symmetry that was imposed by the drive.
Both space and time symmetry broken together.
That's the ticket that gives you the spatio-temporal order. And the way it breaks the time symmetry is the really core part. Its response happens at a period that's longer than the driving period t.
Longer? How?
Specifically, it shows period doubling. It oscillates with a period of 2t. So imagine you kick the system every second, right? Period t equals 1 second.
Okay.
But the system itself only fully repeats its state every 2 seconds, period 2t. Its internal clock ticks half as fast as your kicks. It's fundamentally out of sync.
Whoa, so that 2T oscillation, the fact that it doesn't just follow the T-period drive, that's the smoking gun.
Yes. That persistent oscillation at a subharmonic frequency slower than the drive that keeps going at late times, that's the key signature you'd look for. But actually spotting that in an experiment and being sure it's a real-time crystal phase, that's another story. Super challenging.
Yeah, I bet. How do you actually measure that? How do you know it's not just something complicated, wiggling for a bit and then stopping?
Good question. Your usual tools for spotting, say, spatial order in a crystal need adapting. The key thing experimentally is to watch how local properties, like maybe the magnetization of the spins, evolve over long times. You start the system off in some non-equilibrium state and just watch.
So prepare it, let it run, and measure.
Pretty much. In a normal system that just thermalizes, whatever you measure would quickly settle down to some constant value. Boring. But in a time crystal, you'd see these oscillations, say at 2t in that Floquet example, just keep going and going persistently. Even conceptually, in the limit of a giant system, they wouldn't die out. It's that stubborn refusal to synchronize with the drive lasting forever that signals broken time symmetry.
Okay. Now, you mentioned the source talks about pre-thermal time crystals, too. Are they the same as these MBL ones? Or something different?
Yeah, not quite the same. And this is a really important distinction the paper goes into. Pre-thermal time crystals also show these subharmonic, out-of-sync oscillations, and sometimes they can last for a really, really long time.
Like almost forever.
Maybe exponentially long in certain parameters, like how fast you drive it. So they can look a lot like a true time crystal for practical purposes. But they aren't ultimately stable phases in the infinite time limit. Eventually, inevitably, they will heat up and thermalize.
So they're like incredibly good actors, time crystal impersonators that just keep the act up for ages.
That's a pretty good analogy, yeah. They often pop up when you drive a system really fast. The system behaves, for a long time, as if it's governed by some simpler, effective, static energy landscape. And if that effective landscape would have some broken symmetry,
then the driven system kind of mimics that for a long while.
Exactly. It inherits that behavior, stays out of equilibrium for ages, showing the oscillations. But eventually, the slow heating effects, the ones ignored in that fast driving approximation, they catch up. And poof, it thermalizes.
So how on earth do you tell them apart in an experiment? If one lasts, say, 1 million cycles and the other lasts forever, how do you know what you've got?
That's the million-dollar question. The source points to some key differences, though. Pre-thermal behavior often depends quite sensitively on the exact driving details, like the frequency. And, crucially, it can depend a lot on the specific way you prepared the system initially.
Initial state dependence. Like figure 17 of the paper shows, some starting points last way longer than others.
Exactly that figure. It shows simulations where, change the starting configuration slightly, and the lifetime of those 2T oscillations changes dramatically. A true MBL time crystal phase, though, should be robust. Within that phase, it shouldn't really care how you started it. It should just settle into that time crystalline behavior.
So you need to test Different starting points, different drive parameters, and push to really long times to be sure.
Precisely. It requires meticulous testing of robustness.
Okay, so where have people actually seen these kinds of signals? Have there been experiments?
Oh, yes. There's been some really exciting experimental work on different quantum platforms, trapped ions, nitrogen vacancy centers, NV centers, and diamond, even NMR systems.
The trapped ion experiments seem to get a lot of attention based on the source. What did they actually do and see?
Yeah, those are pioneering. They took a chain of like 10 to 14 trapped ions, held them with lasers. Then they pulsed other lasers periodically to drive the system's interactions. They prepared the ions in a specific non-equilibrium state and then watched how their spins evolved. And they saw it. A clear signal oscillating at twice the period of the driving lasers. 2T. Out of sync.
Wow.
And these oscillations lasted for a decent number of drive cycles, maybe around 100 or so, is a huge step, really showing this kind of behavior was possible to create and observe.
So was that it? Did they find the true MBL time crystal?
Well, according to the analysis in this review, and a lot of follow-up theoretical work that simulated things for longer than the experiments could run, the consensus seems to be that those experiments likely saw pre-thermal behavior.
Ah, the amazing impersonator again. Why that conclusion?
Several things mentioned in the source's analysis point that way. One big one is that strong initial state dependence we just talked about simulations showed the lifetime really varied depending on how you started the ions, just like in Figure 17.
Which isn't what you expect for a robust MBL phase.
Exactly. Also, 1014 ions is amazing control, but maybe still a bit small to be absolutely certain you've got a true many-body phase that would survive in a much larger system. And there were questions about the type of disorder they used. It was randomness in the ion's individual energy levels, which might not be strong enough, theoretically, to fully stabilize MBL and prevent eventual thermalization over very long times, especially because ions interact over long distances, which makes MBL harder to achieve.
So the experiments were groundbreaking. They showed these long-lived, weird oscillations are real, but the detailed physics suggests it was probably the pre-thermal version, not the infinitely stable one.
That seems to be the careful interpretation, yes. But it doesn't diminish the achievement. It showed the path forward. Future experiments need to find ways to engineer disorder more effectively. Maybe randomness in the interactions between ions?
Harder to do, presumably.
Oh, much harder. And they need to push to even longer observation times, which is experimentally brutal and really rigorously test that robustness against initial states and parameters.
Yeah.
That's how you try and cross that line from long-lived pre-thermal to potentially true MBL time crystal.
And the other experiments, NV centers, NMR.
Yeah.
Similar story.
Broadly similar outcomes, yeah. They also observed these period doubling signals lasting for the duration of their experiments, lending more weight to the idea that these long-lived, non-equilibrium oscillating states are definitely achievable across different physical systems. It's just pinning down whether they are truly stable phases that's the remaining challenge.
Okay, it feels like there are tons of things in the universe that oscillate.
Yeah.
We need this super sharp definition to pick out the time crystal from, like everything else that ticks or wiggles.
Absolutely. The paper makes this point to kind of going through a zoo of other oscillating systems that people sometimes mention in the same breath, but which don't meet that strict definition. Stable, macroscopic, conservative, many-body, intrinsic time symmetry breaking.
Okay, like what else is out there that's not a time crystal in this sense?
Well, think about classical stuff first. You can get period doubling in things called parametric oscillators, but they usually need dissipation, energy loss, balanced by driving, to be stable. They're not conservative.
Not closed systems.
Right. Or think about synchronization. Lots of systems can lock their frequency to an external drive, but that's syncsing with the imposed time structure, not spontaneously breaking it with its own rhythm. Then you have things like Faraday waves on liquids, or models of coupled oscillators like the Kuramoto model. These are often open systems interacting with an environment where they rely on simplified mean field descriptions.
What about simple quantum things, or, I don't know, a laser? Lasers oscillate.
Right. We already talked about few-body quantum oscillators, like a single qubit undergoing Rabi oscillations that's not a many-body phase. It would thermalize in a larger system. Lasers are a great example of something with stable oscillations, but they're fundamentally open-driven systems. They need constant energy input to work. Not conservative.
And mean field models, you mentioned those.
Yeah, sometimes you can use mathematical approximations, mean field theory, to make a complex many-body problem look like it only has a few important variables. And those simplified models can show robust oscillations. But it's arguably not capturing the true, complex, collective many-body physics needed for a genuine phase of matter defined in the thermodynamic limit.
So the critical difference for the Floquet MBL time crystal is that it's supposed to achieve this stable, collective, time-dependent order in a closed, conservative, truly many-body setting, all thanks to that magic combo of driving and MBL preventing thermalization.
That's the essence of it. It's predicted as a fundamentally new state of matter, existing far from equilibrium, and it really challenges our standard picture of how closed systems are supposed to behave over long times.
Okay, let's zoom out then. After this deep dive, what's the main takeaway message you want people to have?
I think the core idea is that this concept of a stable, macroscopic time crystal, this perfect, self-sustaining clock embedded in a lump of matter, it's profoundly challenging from a basic physics standpoint because of thermalization.
Right.
But theoretical work, especially focusing on these periodically driven systems combined with many body localization, has carved out a plausible niche where such a thing could exist. A phase with both spatial and temporal order, showing these robust, slower than the drive oscillations.
And the experimental side.
The experiments have been brilliant, really pushing the frontiers of quantum control. They've convincingly shown that long-lived states looking like time crystals, these pre-thermal ones, are definitely real and achievable. But the hunt for that ultimate prize, the truly stable MBL-protected time crystal phase, that's still very much an active, ongoing quest.
And it's fascinating stuff, really probing the edges of what we understand about quantum matter, far from equilibrium.
Exactly. It touches on fundamental questions about complexity, order, and how systems behave over incredibly long timescales.
It does make you pause and think, doesn't it?
Mm-hmm.
Consider the difference between something that just looks like it's ticking forever, maybe because it's really rigid or carefully managed, like those pre-thermal states, versus a state of matter that supposedly inherently possesses this broken time symmetry as a fundamental defining property. Yeah. Stable, indefinitely.
Yeah. What does that conceptual difference, if the latter truly exists, tell us about time itself? About causality, maybe? About the kinds of order that are possible in our universe? It's pretty mind-bending.
A very deep thought to ponder.
Yeah.
Okay, that wraps up our deep dive for today.
And that's a wrap on this episode of What You Don't Know, You Don't Know. If your brain feels a little fuller or like it just stumbled onto something way more interesting than expected, smash that like button, hit subscribe, and tap the bell so you don't miss next week's deep dive into, well, something you didn't even know you didn't know.